Hello. So this is the third day of the simple CTP course on anti-dual equations and integrable systems. So let me continue from yesterday. So from yesterday, we have defined, so our aim in the first chapter is to define anti-self-dual Yang-Mills equation, and it is a condition on connections on a vector bundle. So we have defined vector bundles yesterday. So today, I'm sorry, I'm sorry, let me try to get my pen. Okay. Right. Yep. Okay. So today we continue with connection and curvatures. Okay. So I start by defining connection. So E is a real vector bundle over a manifold M. Then connection on E okay. So let me write out the definition. So a connection on E it is a map. So I would use capital D for it. So it is a map that maps a section of E to a section of this bundle. Let me just write down this product bundle. So it's the cotangent bundle of M and tensor with E. Okay. So D, let me just note. So D is a map that maps a section of E to a section of this product bundle, and we call it an E-valued one form. So it maps a section to an E-valued one form. Let me try. So recall that in local trivialization, a section you can write it as, let me just say, suppose this set EI is a local frame field. The set form is a local frame field, then you can write any section in this form. Yeah, I'm using Einstein summation convention. So S is a SI are component functions, that is functions. Now, for over here, a section of this bundle is an E-valued one form, then you can write it as in this form. Again, this is an element of a framed field, EI, but now omega I, instead of being just a real valued function, now it is a one form, 1M. So these are one forms. Hence, when we, like in computation, when we represent a section with respect to a framed field, on this side, for a section of E, we can represent it by a column vector whose elements are just real valued function. Right? But on this side, an E-valued one form, we can represent it as a column vector one form instead. Right. So a connection is a map a section of E to an E-valued one form, which satisfy the following property, such that it is linear with linear, and it satisfied this product rule I'm going to write down. So if f is a smooth function on M, and S is a section of the bundle, then the connection D act on this, which is a section on E as well, is equal to this. It follows this product rule. So it's the differential of F on a manifold. And then tensor with a section, and then F ds. Okay, so this a map with this property is called a connection on E. So it so now later I will sometimes omit this tensor product symbol, or we just write omega r and ei, but we just have to know that these are one forms now. So next we look at local expression for ds. So this E-valued one form here is called total derivative, total covariant derivative of S. And often, instead of looking at total covariant derivative ds, in many cases, we just, let me just find my pen. We just look at this contraction of the total derivative with a tangent vector field on a manifold. We can do this because this is, let me just go up. So ds is an E-value one form. So you have two parts, so one form on M and E. Then you can, when I say contraction with vector field on M, so this contraction is done on this part, and this just remains. And so we can, looking at this contraction, and it is called covariant derivative with respect to this vector field. So this is just called covariant derivative without total. So just covariant derivative of S with respect to vector field X. So X is a vector field on M, so it's a section of the tangent bundle. And in fact, actually in this form of the covariant derivative with respect to a vector field, it's clear that the connection is a way that we can differentiate sections of vector bundles. So this would be a derivative, like how it changes along direction of the vector field X. Okay. And total derivative just contains the information of in all directions, or information of the derivative in all directions. Right, okay. But for now, I'm not going to look at covariant derivative in particular direction. So I will be just talking about total covariant derivative. But sometimes I will just say briefly that just covariant derivative, but I mean this one. Right. Okay, so now let's look at local expression. And by local expression, I mean with respect to a framed field. So let this set be a frame field, a local frame field. For E over some open set U in the manifold. Okay. Then suppose the covariant derivative of, say, each element in the frame field, each section in the frame field. So this, what is this? This is an E-value one form. So we can write it as in this way. Sum over J. And this is just an ordinary one form on M. We can write it like this just because this is an E-value one form. So it's a section of this bundle, this product bundle. Okay. But now I'm going to put one more subscript, one more subscript I here. Just so this J is a sum, and I just denote that, just label that I'm looking the covariant derivative of EI. Okay, so suppose we have this, where these are some one forms. So many, yeah, some one form. Then we look at the covariant derivative of any section then. So now for any section S that locally you can write it with respect to this framed field like this. Then if you consider ds, the covariant derivative, you have this. And we just use the definition. Yeah, let me just go up. In the definition, you have this property of this product rule. So if we just use this, then with this, so we have SI, which is a function, and this, so I drop the tensor product sign with a section of the bundle. What we have is then just ds, and I'm dropping all the tensor product sign, EI. So this one, the second term, I just use here, we just, so we suppose it for some one form, AI, AJI, so it will be this. My J's. EJ. And then on this term, I'm just changing the dummy index to J, just so that I can write it together. Like this. This is J. This is okay. So we have we have a local expression for the covariant derivative of S like this. And if we writing, so we look at the coefficients and writing it out as a column vector, what we have would be so D is the covariant derivative J, the J component. So these are one forms, and then it's the same as, so I'm writing as a column vector. So these column vector, the entries are the differential of the components is J, and then on here you have, so Aij are the form entries of a matrix. So this is an n by n matrix of one form. And multiply with this Si. So this column. Sorry. Okay. Yeah, so locally we have this expression, and so to summarize, a local representation of D. So ds, you can write it as capital DS, so it's little ds and plus as. And well, when we do computation, we can look at this like this column vector like this, and then this one is here, and this is just n by n matrix multiplied with an n column vector. Yeah. So this A so this A, which is n by n matrix of one form, so it's called connection one form. So it associated to a connection, but it is a local representation. So connection one form, and you have to say that with respect to a frame field. So if you change frame fields that you use, then A will change. Yeah, so this with respect to. And in physics literature, the connection one form is called gauge potential. Okay. Now, over a coordinate neighborhood. So suppose we look at locally, but in a coordinate neighborhood. So you have coordinates, and then you would have this coordinate co-vector field, right? Which is, and if we can write any one form on M in this way, right? In terms of component, in terms of the coordinate co-vector field. Then if we do this, we can write A in the same form like this. Just that the components are now not functions, but then they are matrices. So these are n by n matrices. those entries are now not one form because we have took the one form part on here. So entries are now function. Those entries are function. And this AA and this A subscript A here, this in matrices with entries of function. So in fact, these are the dependent variables of the anti-pseudo-Yang-Mills equation that we will define. Yes, so well, let me say they are called components of the connection one form. And they are actually the dependent variables of the anti-pseudo-Yang-Mills equation. Okay. So before we go and look at, so now we have the dependent variable. So now we have to say what condition is actually that this anti-pseudo-Yang-Mills equation. So anti-pseudo-Yang-Mills equations puts on what condition on these components of the connection one form. Right? But before we look at that, there are a few things I'd like to say about this connection one form. The first thing is, as we discussed here, that a connection one form is something local, that so the expression is with respect to a frame field. So if we change the frame field, this expression will change. So let's see how it changes. Right, so yes, in fact, I'm running slowly again. So let me just summarize that under change of frame field. So suppose from this EI to the set E tilde, okay? Then suppose the over here, the connection one form is A, and let's over here A tilde. So how A is related to A tilde. So if G is the transition functions, if G is the transition function, between these two frame fields, so it's a transition function such that the frame fields are related in this way, then the connection one form A will go to A tilde in this way. So it will be this one. Yes, so A is an n by n matrix and G as well, because it has n by n matrix of functions. It's valued actually in GR and R, so it has an inverse. Yes, and so this A will change to this, you do conjugation, and then with this term add this term. DG just means that each entries of the matrix G, you do the differential of each entries which are function. So you have a one form. Yeah. Okay. And I will have to, I would not have time to write it down. So I will have to ask you to verify this. Okay. And the change of frame field in physics literature, so we call it a gate transformation. So gate is like frame field in that sense, a choice of frame field. So when we talk about choosing a frame field, we just mean a choice of gate in another language. So it is a gate choice. All right. Okay. Now, one of the consequences that the connection one form transform like this, we can show from here. So we can show that under gate transformation, the covariant derivative would change. A local expression with respect to a frame field would change to this one. G is again the transition function of that. And this has an implication, an important implication, that this means the condition that the covariant derivative vanishes, ds equals 0, is gauge invariant. So it's a well-defined condition because it's true in any framed field. Yeah, so this gauge invariant. So we can talk about a connection with this property because it is a well-defined property. So let me give a terminology that suppose you have a connection connection D on a vector bundle, and suppose U is a subset of M, then we would say that a section S of E, we would say that this section is covariantly constant covariantly constant on U if ds is 0 on U. Yes, and as I've mentioned that this condition, this property of this section, it is covariantly constant on U, is well defined because it is gauge invariant. So now let me try to define the anti-Self-Young-Mills equation. But to define it, I will need to define a curvature of a connection. Now let me just jot it down roughly that a curvature, or we use f, of a connection is actually d squared because the connection is an operator. So it's in d squared, so d composite with d. But to write about this, and So it's another operator. But if you think of this curvature acting on a section, yeah, by this definition, you will have this. But over here, the covariant derivative of a section is an E-valued one form. So this is a one form, but we have only defined connection as an operator on a section of E, not an E-value one form. So before we define it, I will have to say about we need to extend this operator to act on E-valued one form first. Okay. Okay, so a connection, we can extend the action of connection on E-valued one form. In fact, any K forms or any forms of any order. So it defines, and this operator we call covariant exterior derivative. The connection defines a covariant exterior derivative for E valued K form. And this operator will map an E-valued K form, which is a section of this bundle, to an E-valued K plus 1 form. So this K plus 1. So define this, and the covariant exterior derivative, we defined it so that it has a property that is satisfied this another product rule. That if you have this wedge product, sigma is an E-value K form. So this is an element. This. And alpha is just an ordinary differential form. Say an L form. So it is a section of this bundle. Okay, so this is just an L form on M. Right? And if we, the covariant exterior derivative on this, we'll have to satisfy this product rule. So D alpha with sigma. Okay. Right. And in fact, there is a theorem which says that for a connection, there is really a unique extension of a connection that acting on an E-valued K form to K plus 1 form with this property. And it is an extension of the connection we defined before. And let me just, for our purpose now, just to define the curvature, let me just write local representation for this map. And I will abuse the notation and always use D to just mean connection that acts on a section of the vector bundle and also this covariant exterior derivative. So local representation. So d sigma is, it can be shown that it's here. This is just the same A, the connection one form before. But sigma is a E valued K form. Okay. Right, so let me now define curvature of the connection. I have previewed briefly that the curvature, I use symbol F of a connection D on a vector bundle E. So it is the map F, which is just the square of the connection. So it is a map that maps a section of E to, well, do it once, it will be an E valued one form, and do it again with covariant exterior derivative we just defined, it will be E valued two form. Okay, so this is curvature. So, let me write it in a different color just to note that you have that F maps a section of E to E value two form, to an E value two form. Okay, so now let's look at local expression of F. So locally, by locally, I would mean with respect to a framed field, a local framed field. So we can derive it just by look at, so when F acts on a section S, so by definition, it is just this. And then we just use the local expression for the covariant exterior derivative, because this is an E value one form. So we have this, which is up there. It's here. So we just use this a local representation. So we will have sorry. D of ds and now we already have the expression for ds, which is this one. Then it follows, let me just write, it follows that we will actually have, if S is this AFHA, hence we conclude that local representation of F is given in terms of the connection one form. So A is, if we think local representation, so A is an n by n matrix of one forms, and dA would just mean you just do exterior derivative to each entries of A. So you have a matrix of two forms. And for this one, you just multiplied A with the matrix, normal matrix multiplication. But then when each entries, when the entries of A are multiplied, then we use wedge product. So F is local representation. It is an n by n matrix of two forms. And under a chain of gauge, so under a change of local trivialization of frame field or gauge, they are the same thing. Chain of local trivialization on E. With the transition function G, you have that the curvature will change to a new one by conjugation, like this, where G is the transition function. And over here, what I'm written here, I'm using the same notation as what we have above. Here that if we change from a frame field E to E tilde, and where the transition function G is the one that relates the two frame field like this, then yeah, my F here is with the frame field E, and this F is E tilde. So they are related by this conjugation. Okay. And an important things about this is again that the condition F equals 0 is invariant under gauge transformation. So it is a well-defined condition. So it is an invariant condition. And it is a well-defined condition on a connection. Then we have a word for it that we say that a connection D is a flat connection. So it is called a flat connection if its curvature vanishes. And if it vanishes in one frame with respect to one frame field, then it will in all. Okay. There's one last thing I would like to say about a curvature before we go on to anti-subdo-Young Mills equation. Let me just look. Okay, there are two more things. Okay, first thing is that, let me just note here without proof that in fact this curvature is actually a section of this bundle here. So this is the bundle of two forms and endomorphism of E. And a section of this bundle, we call it E. Sorry. We call it NE value two form. Right? Where this bundle NE is it is a vector bundle over M whose fiber at each point P and M is the vector space of all endomorphism of the fibers of all linear map. From the fiber at P to itself. Right. And so F is a two form and with value in this bundle. And actually, we can also extend the action of the connection. At first, we define the connection. Maybe I can go up. So first, today, we define a connection as a map that acts on a section of E, and then we can extend it to covariant exterior derivatives act on E-valued K-forms. And actually, it can be extended still to act on endomorphism value differential forms like this. Let me just write down the definition. The action of a connection D on E can be extended to endomorphism of E in E valued K form. And the curvature is a two form. And this action, let me just write down local formula for it. So it is given by local formula like this. D and omega here is an NE valued K form. Okay. So it is given by the omega, and then so you can think of locally, you can think of NE value K form as matrix. And if E is a vector space, I'm sorry, vector bundle of rank N, of rank capital N, then this K form will be can be represented by n matrices whose entries are now k-forms. Right. Yes. And this is our connection one form, the same one. Okay. I'm actually kind of hurried to give this formula. Just I want this formula because I want to state this theorem, which is important on curvature and will be important for our anti-pseudo-Yang-Mills equation as well. That is this theorem here. Is the Bianchi identity. Identity on the curvature that df and df is defined with this. Yes, df defined like this. If f is a curvature, if f is the curvature of a connection on the vector bundle, then df is 0. So this is an identity for curvature of any connection on a vector bundle. And this can be proved, just use the local expression here. So you just write it out and we'll see that it is 0. So use local expression. Okay. Right. So we nearly, okay. So let me end this first hour. And this will end section 1.1, and then section 1.2, I will talk about anti-pseudo-Yang-Mills equations. But lastly on here, I have to talk about a structure group or gauge group, which this is also important when we want to define anti-pseudo-Yang-Mills equation. It is an information that we need to specify, especially when we look at reduction to integrable system. So structure groups or gauge group, the means are the same. So what they are? So normally, in general, the transition function takes value in it. We define it. It is a function on the overlapping region and to GR in R. So GR in R. Yeah, so it takes value in GR in R, the general linear group. But sometimes we want to, we may want to strict that we will only consider transition function which takes values in a subgroup of the general linear group instead. Right? And we call this subgroup structure groups or gauge group. Okay. So sometimes we restrict the transition functions so that it takes values. I would just say that it's a function. So when it evaluated at a point P in its domain, it is in a subgroup of the general linear group. So D is a subgroup. Okay, for example, this is one of a popular example that if we look at the tangent bundle, so E, that vector bundle is a tangent bundle over a manifold. So suppose that it has an additional structure, say it has a Riemannian, the tangent bundle with a Riemannian metric. Riemannian metric. Then if it has a Riemannian metric H, we can they always exist orthonormal frame fields, at least locally, right? Then we just say that we will just restrict instead of we allowed any framed fields, we say that we restrict to orthonormal frame fields. Restrict. Then if we do that, then the transition functions can't take values in the values of transition function can't be any invertible matrix because it will not change orthonormal frame field an orthonormal frame field to another orthonormal frame field. So we wanted to take value in the orthonormal group. So then this GP has to be in the orthonormal group ON, okay, which is a subgroup. Okay, for example, like this. And suppose this happens, then suppose in what we consider, we have the structure group, which is not GL and R. Is some G is a subgroup. And in fact, let it be a Lie group too. Okay. Then we may impose some condition on the connections that we will consider. So we may impose a condition on connections on E, that we just say that, okay, we will only consider connections that satisfy this condition. And the condition will be so that the components of connection one form, and thus because it will relate to components of the curvature, so that these components take values in the Lie algebra of G. And in computation, like especially in reduction to integrable systems, we will consider connection which satisfy this, which is compatible like to the structure group like this. Yes. So we would say D is compatible. Okay. And let me, I think I have defined these components of a connection. Just wait. Yeah, that recall that the connection one form in a coordinate neighborhood, you can write it like this. So this is A subscript A here. And for FAB, it is from this. Then for this one, if we write it, because F is an endomorphism value 2 form, so it is a 2 form. And if we write it in terms of the wedge product of the co-vector field on the coordinate co-vector field on the manifold, like this, then this FAB are these coefficients here. And in fact, we can work it out from the relation between F and A, that since F is dA plus A vector, then it will follow that FAB is given like this. Okay. When we write down explicitly what anti-pseudo-Yang-Mills equation is, we will have to use this expression as well. Right. Okay, and this is about 1 hour, and I end the section. So I think let's have a break. Let me look at the time. Okay. 15. Let's have 5 minutes break. So I will start again at 7 past 3, and we will define anti-pseudo-Yang-Mills equations. Okay. Right. So let's have a break now. All right. Okay. Let's continue. Okay. Oh, actually, I'm sorry. I go to the wrong notebook. It has to be this one. I'll have to add a page. Okay. So this is 1.2. Okay. But now I can't. I'm sorry, I have to try my pen. How do I go? Right, sorry. Okay. So we finished with vector bundles, connections, and curvatures. And now, what is anti-pseudo-Yang-Mills equation? Equations. Okay. So to define, so I will first define what I mean by anti-pseudo. So there is a duality, and that the duality is with respect to Hodge-star operator. So this is Hodge-star operator. Okay. So the definition. So our setting now, the manifold will not, before this, we just look at vector bundles over a smooth manifold, and it's just a manifold without any structure. But in order to define anti-pseudo-Yang-Mills equations and Hodge-star operator, we need that M, there is a metric structure on M. So Mg, so let this be a pseudo-Riemannian manifold, and in fact, oriented. Pseudo Riemannian. Riemannian. Let's say n-dimensional manifold. And G is pseudo-Riemannian metric. I'm sorry, I kind of abuse notation because before this G refers to transition functions of the vector bundle. But I hope that there's no confusion according to the context, right? But here, let me just use G for pseudo-Riemannian metric as well. Okay. Then the hot star operator. Is a map. So it maps. Let me define hot star operator on a manifold first without any vector bundle for the moment. And so it maps a K form, a smooth K form to n minus K form, where n is the dimension of the manifold, m. Yes? And this map can be defined locally like this. So it is defined locally by and locally and in a coordinate expression as well, that it's when it acts, this is star for the hot star operator. So when it acts on a K form, which is the wet product of coordinate one form, coordinate covector field, it is given by this. There's some constant weight and square root of determinant of the matrix GAB, and let me just say that the determinant of these matrix whose entries are the coefficients of the pseudo-Riemannian metric with so the coefficients when we write G with respect to this coordinate one form. So maybe I just write here that we just write G like this. Yeah, with the same coordinates, one form. And this coefficients form an n by n little n by n matrix and give a determinant and the absolute value. And then these are components of the inverse metric of G. And I'm sorry, I don't think I have enough space. Let me go down here, but it is continue. Okay. So this is a K form, and the hot star is an N minus K form, which can be written in minus K form from here. And this epsilon is an alternating symbol. And I'm using I-star summation convention again, that summing over C1 to CK, and then B1 to BK to BN minus K here. This index AB just to indicate that this is a matrix, that's all, but it's so but the epsilon, this A1 to AN is the alternating symbol that it is equal to 1 if the indices A1 to AN is an even permutation of 1 to N. One, two, three to N, and minus 1 if it is odd permutation. Right. Okay, let me just give example that you can try to verify using this formula. That, for example, if M is just R3 with Cartesian coordinates, and G is the flat metric given by this. Okay. And the orientation is determined by the volume form. Just write down. It's a volume form. Now, with this G, we can, so we have what we want to use this formula, right? So in this case, GAB, the G is just the matrix GAB is just identity matrix. And the determinant then it's just 1, right? So here it's just 1. And then the components of the inverse matrix, the inverse matrix will be just identity as well. So you have this. And if you put this in, you will see that the hot dual of dx will be dy wedge dz. And dy will be dz wedge dx. And dz will be this. And they asked you to verify this. And but then if we change it to, it's the same, M is R3 as before, but then if G is instead of this Riemannian metric, it is the Lorentzian one. Then you will have that dx is minus divided by with this. All right. Let me just go up here. That from this local formula, we can write down the expression for the components of the Hodge duo of a K form. So let me just write it out. So it can be shown that in components, suppose alpha is a K form, and we can write alpha in components like this. I mean, we can write alpha with respect to coordinate covector fields like this. So alpha, say B1, BK, and this is dx B1 with dx BK. Okay, and so for the Hodge duo of alpha, it will be n minus k form, and the component like this components here. So the components a1 to an minus k, and this it follows it's followed quite easily from this formula here. This is K fact. Epsilon A1 to A minus K B1 to BK GB1 C. Yeah, so the components of the Hodge duo is related to the components of alpha in this way. Right. And, okay. I'm writing it out because when I want to write Andy-Seldon-Young-Mills equations out in coordinate, we can use this formula to write it down. Okay. Right. What's the one last property I'd like to mention is it is an important property that when you do the Hodge star operator, when you apply it twice, alpha, it will be proportional to alpha with this factor. Where alpha is a K form on M. For T here, what is T? T here is the number. Maybe just write down number. Is the number of so related to the signature of the pseudo-Riemannian matrix, the number of -1 in the expression of GAB and in orthonormal basis. Because if we use orthonormal frame field, if we use orthonormal frame field, then the metric will be of the form, the components will be diagonal matrix, and we just have +1 and -1 over here, and the number is the -1 is this is t. Just one. Okay. Now, the hot duo of a K form, if suppose M is four, the manifold M is 4 dimension, and if we consider two form, then from the definition, so if M is of 4 dimensions, so N is 4, and if K is 2, so 2 form, so we see that hot star operator maps a 2 form to a 2 form, right? So it's with particularly simple. So this is the next part. Self-duality of, maybe it should start a new page actually. Let me just do that. Self-duality of two forms on 4-dimensional manifold. Okay. So if we consider a manifold M to be 4-dimension, then the hot star operator would map a 2 form to a 2 form. And suppose we will only consider the metric G. So M is still pseudo-Riemannian, but if we let the metric be either Riemannian or neutral signature, and by this I mean that means that in an orthonormal frame field, GAB, this matrix is the diagonal matrix of 1, 1, 1. So this is identity matrix. This is for Riemannian, but signature. But if it's neutral, you have say 1, 1. Okay. So if we say that we will look at G be either Riemannian or neutral, then from what we had before, I have to go to, from what we had here, so T is now either 0 or 2. So this is just +1. And then, well, K is 2 form. In minus K is also 2. So you have that star twice, the hot star operator apply twice, it's just identity. Right? So star alpha is just alpha. Then this is just the identity map. And this implies that it has eigenvalues plus and minus 1. Then we can consider two forms that satisfy this property. Then we can consider two forms that it is an eigenvector of say 1, so you have this, and if it eigenvector of -1, you have this. And then we say that this is self-dual and this is anti-self-dual. Okay. Let me write this down. So on four-dimensional Riemannian or neutral manifold, we have a definition of self-dual or anti-self-dual two forms with respect to Hochstar operator. So we say that a two form alpha is said to be self-dual if star alpha is alpha, and we said it's anti-self-dual. So this abbreviate to SD, and this is ASD. If star alpha is minus alpha. Okay. In fact, we can see that any two form can be written as a sum of SD and ASD two form like this. Just in fact, even for any two form alpha, you can write it as a sum of SD part, which defined like this, and the self-dual part. So it follows that the vector space of two forms decompose into the direct sum of vector space of self-dual two forms and anti-self-dual two forms. Right. Let me again write down the example for you to verify that. For example, let's say M is R2, 2. By this, I mean the set, it is R4, but then it has a neutral signature flat metric. So G is, suppose the coordinates on this R2, is X0 to X3. So G is, let me set this. And the orientation is specified by this volume form. Then in components, and this is just follow from the expression for the components we just looked earlier. So this star alpha AB is epsilon. This is again just the alternating symbol. Okay. Then from this expression, you can verify that alpha will be anti-self dual if and only if the components, so it is the same condition that the components satisfy this system of equation. That alpha naught 1 is the same as alpha 2, 3. The component with respect to x naught to x3. Yes. Okay. Anti-self dual. This is the way, this is the meaning of anti-self dual, the word anti-self dual in anti-self dual Yang-Mills equation. But for anti-self dual Yang-Mills equation is actually the anti-self dual condition, not on just two forms on M, but on the curvature of the connection, which is an endomorphism value, which is the NE value two form that we looked at. Right, so let me just write it down and we will finish chapter 1 now. So add more page. So self duality of curvature two form. So now the setting is now with a vector bundle, but the base manifold is strictly 4-dimension. And because we are going to define hot star operator, so we require it to be oriented pseudo-Riemannian with the metric G, but pseudo-Riemannian. Let me just say pseudo-Riemannian. It will be either Riemannian or neutral. Okay. So with this, we can define a hot star operator on M. But now we also have a vector bundle over M of Rankine. Okay. Now recall that the curvature F curvature of any connection on E connection D on E, which is defined as D squared. So it is an NA valued two form. So F is a section of this bundle. This is what we had before. then we can extend the hot star operator on M to act on the curvature F as well. So we extend the hot star operator so that it acts on NE valued K form. So it's a section of this. To ND value for minus K form, because we are in 4 dimension. So we extend it simply by that an element here, it is a linear combination of terms like this, that the tensor product of a K form on M with a section of NE. And then we just say that the hot star operator will act on alpha, on the part of the K form on M. Like this. And then, so any element in here will be a linear combination of this. And then we define the hot star acting on this term like this. And then we just extend to any element by linearity. And then extend by linearity. Over C infinity, over smooth function. Okay. Now, but locally, the formula for the hot star operator of the curvature F will be the same like what we had for an ordinary 2 forms on M. So let me just write that. So locally, if we write F like this, then the hot duo of F, which is also a 2 form, the component is given by the same formula like what we had before, which is this one. Just write that. Okay. The only difference is that before we had this same formula with alpha instead of F, right? The formula is the same. The only difference is that before the components, alpha A, B, the components are just functions on M. But now the component set of F, these are n by n matrix of function. So FAB is actually n by n matrices of function, whose entries are functions. Okay, but the formula is the same. Okay, now this is the end of the first chapter. That now I can say what the anti-pseudo-Young-Mills equation is. So the anti-pseudo Young-Mills equation is just the condition that the curvature of a connection is anti-self-dual. So just here, just this one. That's all. But then when we write this equation down in terms of components, then because the components of the curvature can be written in terms of the components of the connection one form. You remember, I think we had this before. Then this equation will just be a system of equations for the components of the connection one form, this A here. Right, okay, I think so I have said what anti-self dual in the name means. So this just means anti-self dual of the curvature with respect to hot star operator. But now for the word Yang-Mills, let me just give a brief note that. So why we call it anti-self dual Yang-Mills? Because it is just the condition that the curvature of a connection is anti-self dual. But the name Yang-Mills comes because, in fact, the full or the Yang-Mills equation. So what it is, it's actually an Euler-Lagrange equation of, there is a functional called Yang-Mills functional, and this is the Euler-Lagrange equation obtained by the variational principle. And it's actually in this case of, is d star f equals 0. Let me just write, it is the Euler-Lagrange equation of a functional on vector bundle called the Yang-Mills functional. Okay, but now since we know that the Jacobi identity, this is what we had before, the Jacobi identity, that df is 0. This is true for any connection. Jacobi identity. Since this holds for any connection, it follows that a solution, if you have a connection that is a solution of anti-self dual Yang-Mills equations, so if you have a solution of the anti-self dual Yang-Mills equation, then, well, you put star f in here, so you will have the Jacobi identity. And the solution of this is also a solution of the full Yang-Mills equations. So that's why this equation is called anti-self dual Yang-Mills equation. Okay. So this satisfies. Okay, right, so this is the end of chapter 1. Now, I have about, I think today, sorry, I have about 10 minutes left. I really need to continue because tomorrow is the last day and there are 2 more chapters, but I will see how much I can get. Right, so the second chapter. So here I would like to talk about example of reduction of anti-self dual Yang-Mills equation, because the whole thing is, the whole course is about relations of anti-self dual Yang-Mills to lower dimensional integrable systems, that the integrable systems can be realized as reduction of the anti-self dual Yang-Mills equation. So let's look at two examples, I hope. And so I think, and I hope from the example, you would see some features of what a reduction means. And also, I would like to talk about lax pair, which is an integrability feature of anti-pseudo-Young-Mills equation. Okay. So first, looking at example first. Let's just copy this. And in this part, I followed mainly the book by Donowski and Mason and Woodhouse. Okay. So first, so far I have only talk about real vector bundles, but in fact, we can have anti-pseudo-Young-Mills on complex vector bundles as well. So in two of my example, one will be on the real vector bundles that we have done, and then another example will be on a complex, which I think it has to be tomorrow. But let's see. So the first one, we look at anti-pseudo-Young-Mills on real vector bundle. Okay. And the example one, this is an example of an integrable system, which is a reduction of anti-pseudo-Young-Mills. And the equation I want to talk about is the twistor equation, which is this equation here. My z and z tilde are real coordinates, but I use z because later we will have these coordinates as complex, but now they are real. Okay, this is twistor equation, which is a partial differential equation on two independent variables, x and z and z tilde. And this, I want to show you that this is a reduction of anti-pseudo-Young-Mills equation on R22 again. So flat metric in neutral signature. But I think before this, I have written the flat metric in Cartesian coordinates. But let me change it to, this is called double null coordinates. Then the metric is of this form. And the orientation or coordinates are real. Now, the orientation is determined by this volume form. Okay. Double now coordinates. Okay. And let me just write down what anti-pseudo-Young-Mills equation is. So E is a real vector bundle. Real vector bundle of ranking. And suppose we write the connection one form. Locally, we can write it in terms of coordinate one form like this. But if we adapt to this double null coordinates, this one will be, for example, where each components are n by n matrices. Well, each component is an n by n matrix of functions. And these will be the dependent variables of the anti-pseudo-Young-Mills equation. And let me just write f. So from this, if we can look at components of the curvature f. And here you will have components in these coordinates. So there will be terms like w tilde, etc. on here. Okay. Now, let me just write down anti-pseudo-Young-Mills equation, and I think the time is over for today. So the anti-pseudo-Young-Mills equation that star f is minus f. Then using the from the coordinate expression, like the expression of star f in components, you can show that this is the same as this system of equation, that the components of f in like the one that is at w has to be 0. And this is 0. Okay. This has to be verified, but if you compute this is, so this is the anti-pseudo-Young-Mills equation in this case. And if we write it out using, if we use that f AB is given in terms of the components of the connection one form by this. We will have that anti-pseudo-Young-Mills equation is a system of 3 equations here. Let me just write it out, and I think this is the end for today. I'm just writing this equation with this, so it's just this one. And I continue with the other two, so we have this. Okay, and the last one. Okay, and I think that the time is over, 0. So I think tomorrow I will show how the Tiseka equations up here can be realized as reduction of this system. Okay, and I would try to see what I can do to cover as much as I can tomorrow for the last day. Right. Okay, so I think so this is for today then. So I end this video now. So thank you.